Hi everyone, this is the topic Sequences and Series. It's a topic for the International Baccalaureate course Maths Standard. In this topic we're going to go through number sequences, the general term of a number sequence, arithmetic and geometric sequences, series, and then arithmetic and geometric series. So a number sequence is a list of numbers that follow a rule or a pattern, and each number in the sequence is called a term. And we use the following notation. So U1 is the first term, UN is the nth term or general term. And if we describe a sequence, we can either state the rule or describe the pattern in words. Now once we find the pattern or the rule for a number sequence, we can continue that pattern. So here's an example. Find the next two terms in the sequence 5, 20, 80. So first thing we've got to figure out is what's happening to this term in order to give this one. And we've got to make sure that we're doing the same thing each time. So then what happens to the 20 to give 80? I'm hoping you can see that we have multiplied by 4 in each case. So we can write, the pattern starts at 5 and then is multiplied by 4 each time. And the next two terms must be 320 and then 1280. The general term or the nth term of a sequence is the rule that defines the sequence. And this is how we write it, in curly brackets. So this is the formula, if you like, that will generate this sequence. We put n equals 1 in, that'll give us 1. Put 2 in, 2 2s are 4, take away 1 is 3. Put 3 in, then put 4 in, put 5 in, etc. You may have seen it written like this, where this is the first term, second, third, fourth, nth, and then this is the value of each of the terms. So the first term is 1, the second one is 3, the third one is 5, the fourth one is 7, and the nth term is 2n minus 1. And you did a lot of this in year 7 and 8 where you were given this table and had to figure out what the rule was. Now there are two specific types of sequences that we're actually going to study. They're arithmetic sequences and geometric sequences. Arithmetic sequences have a common difference and geometric sequences have a common ratio. So let's start with arithmetic sequences. When we add or subtract the same amount each time, the sequence formed is called an arithmetic sequence. And that constant amount that's added or subtracted is called the common difference. And we use the letter D to denote the common difference. Let's have a look at how we might work out the nth term of an arithmetic sequence. Consider the sequence 1, 4, 7, 10. Suppose we wanted to know what the 40th term in the sequence was. We can see it's going up by 3 each time. We could just sit there on the calculator and go plus 3, plus 3, plus 3, plus 3, but we need a quicker way. Now can you see that we're starting at 1 and we're adding 3 each time, but when we get to the fourth term we've only added 3 times. So if I want the 40th term, I want to add 39 lots of 3. So I'm going to start with the 1 and then add on 39 lots of this common difference. So our 40th term is 118. Let's look at it more formally. Here's the first term. The second term will be the first term plus the common difference. The third term will be the first term plus 2 lots of the common difference. And this is going to build us a formula. So our nth term is going to be the first term plus n minus 1 lots of the common difference. So that's our first formula that we're going to learn. Let's see how we use it. For the sequence 4, 9, 14, 19, firstly show that the sequence is arithmetic. All we need to do here is show that there's a common difference. We just find the difference in the pairs of terms. We do 9 take away 4 is 5, 14 take away 9 is 5, and we can also say this difference here is 5. So because we have a common difference, the sequence is arithmetic. Now we want to find the 25th term, so we're going to put it into that formula. So U1 is 4, D is 5, and N is 25. So I've got U1 plus N minus 1, I've taken a shortcut here, times D. In the calculator gives us 124. and then find the general term. So in this case, we're just going to put in 4 for the first term and 5 for the common difference, but we're going to leave n alone like this. And we'll tidy that up, so expand these brackets. And then our general term is 5n minus 1. Here's another example. What value of k will make the sequence k, 4, k minus 3 arithmetic? I'm going to use a similar technique to the one we did on the previous slide, where we were trying to show that the sequence was arithmetic. We found the difference in the pairs of terms. In this case, we're going to say if this minus this equals this minus this, then the sequence must be arithmetic. So I'm going to do k minus 3 minus 4 equals 4 minus k. And this is just an equation that I'm going to solve. So collecting your terms on the correct sides, k is equal to 11 on 2. And I could substitute that back in and show that we had a common difference. Sometimes we'll get a simultaneous equations question like this. Find the general term for an arithmetic sequence, un, if the fourth term is 18 and the 11th term is 67. You could do this just using your general problem solving skills. You don't have to use simultaneous equations, but this is a method that will always work. What we're going to do is put in our formula here and make it equal to 18, and the same here. Now, we don't know the first term and we don't know the common difference, but we do know n is 4 in this case. And remember, it's u1 plus n minus 1 d. So there's our first equation. u1 plus 3d is equal to 18. Can you think how we might write this one? It's going to be u1 plus 10d equals 67. And there's our two equations. You can solve them on the graphics calculator if you want to by going into the simultaneous equations solver. But if you're in the non-calculator paper, you don't have that luxury. So let's revise how to do this. We're going to use the elimination method. So I'm going to subtract. I'm actually going to subtract from the bottom up so I avoid negatives, which is perfectly fine. I'm not going to spend time rewriting it with this equation on top. I'm going to go 10d take 3d is 7d, and 67 take 18 is 49. Divide both sides by 7, and d is equal to 7. If you did it this way, all that will happen is you'll get negative 7d equals negative 49, and the negatives will cancel out, so you get the same answer. Don't stop here. We also need to know what u1 is. So substitute your 7 back into either one. Let's put it into here. So u1 plus 21 equals 18. So our first term is negative 3. So have we answered the question? No. Find the general term. So we're going to need to put it into our formula. u1 is negative 3, d is 7, and n is going to be n. So just tidying that up, there's our general term. un is equal to 7n minus 10. Okay, so here's an arithmetic sequence problem. So this is where it's going to be a real life situation. Claire is learning to drive. Her first lesson is 30 minutes long. Her second lesson is 35 minutes long. Each subsequent lesson is 5 minutes longer than the lesson before. Why is this an example of an arithmetic sequence? So that's exactly like the question that we did a couple of slides back, where we wanted to prove a sequence was arithmetic. So all we've got to do here is find a common difference, and it actually tells us, doesn't it? Each subsequent lesson is 5 minutes longer than the lesson before. So there is a common difference of 5 minutes. How long will Claire's 21st lesson be? Okay, so now we want to find the 21st term. We're going to use that formula u1 plus n minus 1 in brackets times d. d is 5, u1 is 30, and n in this case is 21. So substituting into the formula, we get 30 plus 20 times 5, which is 130 minutes. C, which lesson will be 100 minutes in length? Now this time we need to solve an equation. This time we don't know n, but we know the value of the term, that's 100. So substituting it in like this, you can see how I've got the 100 sitting where un normally would be. u1 is still 30, n we don't know, and the common difference is 5. solve this on your calculator or by expanding. N minus 1 is equal to 14, and so n is equal to 15. Let's move on to geometric sequences. So in a geometric sequence, there's a common ratio, so a multiplication, this time instead of an addition or subtraction. Each successive term is found by multiplying the previous term by a constant. And this common ratio is denoted by R. So here's an example. 1, 3, 9, 27 has a common ratio of 3 because we're multiplying each time by 3. Let's have a look at the nth term of a geometric sequence. So if the first term of a geometric sequence is u1 and the common ratio is r, then the sequence is going to be u1 and then u1 multiplied by r and then u1 multiplied by r squared. Can you see commonality with our nth term of an arithmetic sequence? R is the amount that you're multiplying by is always one less than the term. So this is the first term, second term, third term. Which brings us to our general or nth term is going to be un equals u1 r to the n minus 1. Here's an example. For the sequence 8, 4, 2, ... show that the sequence is geometric. So similarly to the way we did it for arithmetic, instead of subtracting, we're going to do division. So we're going to go 4 over 8, which is a half, and then do 2 over 4, which is also a half. So u2 divide u1 is a half, u3 divide u2 is a half. So since there is a common ratio, the sequence is geometric. Find the general term. So now we're going to use that formula. We know u1 is 8, we know r is a half. Okay, we're going to do it like that. Don't be tempted to try and multiply this and get 4. Okay, this is raised to the power of n minus 1, and this is not. So that's actually as good as it gets. 8 times a half in brackets to the power of n minus 1 is our general term. Find the 10th term. So now we're going to use the formula that we just found and substitute in n equals 10. And so it's 8 times a half to the power of 9. Put in the calculator, we get 1 on 64. Which term is equal to 1 on 256? So this is similar to the question we did with arithmetic sequences where we're given the term and we don't know n. So using our formula, I know that our general term is going to be equal to 1 on 256. But let's bring this 8 over here as a division. So a half to the power of n minus 1 is equal to 1 over 2048. And just by using guess and check, n minus 1 is equal to 11. So therefore, it's the 12th term that's equal to 1 on 256. Okay, we did a question like this earlier, but we're going to have an added bit this time. What value or values of k will make this sequence k, k plus 1, 2k minus 1 arithmetic, and then we're going to do geometric. So if it's arithmetic we're going to do this term take this one equals this term take this one. Be careful here, you want to subtract all of that, so make sure you put it in brackets. Tidying this up, I'm going to get k minus 2 is equal to 1, and so if k is equal to 3, then the sequence is arithmetic. Let's see if that's true. Substitute the 3 in. Well, that's going to make the first term 3, the second one 4, and the last one, 2 3s is 6, take 1 is 5. It is indeed arithmetic. Okay, how about geometric? So this time we're going to go 2k minus 1 over or divided by k plus 1 equals k plus 1 divided by k. We're going to cross multiply here, and that's where our brackets are going to come in. So I'm going to get 2k minus 1 multiplied by k equals k plus 1 all squared. I've expanded those out. Okay, so 2k squared minus k equals, this is k plus 1 all squared, expanded. Now taking everything over this side, I'm going to get k squared minus 3k minus 1 equals 0. And that can't be factorised, so I need to put it into the quadratic formula. And tidying it up, I get two answers, 3 plus or minus the square root of 13 all over 2. I'm not going to substitute them back in to show that it's geometric, but there's our answer. There's also a simultaneous equations question that we can do with geometric sequences, and it looks like this. Find the nth term of a geometric sequence whose third term is 2.42 and fifth term is 2.9282. So again, we're going to set up, use our general term to set up two equations and then solve them simultaneously. So it's going to look like this. We don't know the first term and we don't know r. But this is the third term, so n is 3. So you can see why I'm getting 2 here. So u1 r squared is 2.42. What about this one? It's going to be u1 r to the fourth equals 2.9282. Now, we can't do our normal thing that we do where we subtract. It's actually not going to work. It won't cancel anything out. What we're actually going to do is divide both sides. And I'm going to go from the bottom up again, like I said we did before. I'm going to do this one divided by this one is equal to this divided by this. Okay, so when I do that over that, the u1's cancel out. Actually, I might write this for you. u1 r to the fourth over u1 r squared. And you can see that they cancel out. And when I divide pronumerals that are the same, I subtract the indices. So I get r squared is equal to this division here, 2.9282 divided 2.42, which gives me 1.21. The last thing we've got to do is the square root of both sides. And be careful here because you're going to get two answers. So square root of 1.21 is plus or minus 1.1. Now that's not the whole story. Remember, we've got to find u1, so we're going to substitute that plus or minus 1.1 back into the first equation. So that's going to give us u1 times, I've just put the plus or minus in here, 1.1 to the power of 2, because I know that's going to cancel out. When we square a negative, it's a positive. Squaring that gives us 1.21, and dividing both sides by that will give us 2. So the first term is 2. So the sequence could be 2, 2.2, 2.42, 2.662, or it could alternate with positives and negatives. 2, negative 2.2, 2.42, negative 2.662, etc. So if we want to write the nth term, we have to account for this. So we're just going to write it like that. So u1 could be 2 times 1.1 to the n minus 1. Or it could be 2 times negative 1.1 to the n minus 1. So two possibilities. So here's a geometric sequence problem. In 1859 in Australia, 24 rabbits were released into the wild for hunting, and their population exploded. By the beginning of 1865, it was estimated that there were approximately 22 million rabbits. Now, population growth is an example of a geometric sequence. So taking u1 equal to 24 and u6 equal to 22 million, find the common ratio r and the expected population at the beginning of 10 years. Write your answer in the form a times 10 to the k, where a is between 0 and 10 and k is an element of z. Now, have you seen this before? All this means is write it in scientific notation. But remember, the IB is uses very formal notation, so you've got to be used to seeing things like this. This means we want it written as a number times 10 to the power of, which is definitely scientific notation. The beginning number has to be between 0 and 10, but not equal to either of them. And this power has to be a whole number. Remember, z is a set of integers. It can be negative or positive or 0, but it has to be a whole number. Okay, so we're going to write our answer in scientific notation. Okay, back to the question. Okay, we've got u6 is equal to 22 million. We happen to know u1 in this case is 24, so let's substitute that in. 24 r to the 6 minus 1 equals 22 million. Let's solve for r. So divide both sides by 24. I get r to the fifth is equal to 916,666.67. Now to find r, I need to do the fifth root. And just do that on your calculator. You find the button that has the little bit out the front for the square root, and do the fifth root, and we end up with 15.6. Now, just to put this into perspective, our population growth at the moment is only 1.07%. So if we start off with 100 people, we end up with 101 and a bit people at the next year. This is huge. Okay, it's multiplying by 15 each time. So it started off with 24, and by the end of the first year, you had 24 multiplied by 15.6. One of the reasons that it happened in Australia was because the climate was so favourable, the rabbits could breed 4 times a year. Plus they had no known predators, so it caused a huge issue. So huge growth rate. If we want to write the expected population or find the expected population at the beginning of 10 years, we're going to do 24 times r to the power of 9, and your calculator will probably put it in this form anyway, but it's 1.31 times 10 to the power of 12. And that's a huge number. I mean, let's have a look at it. It's 131 with 10 zeros after it. So it's in the trillions. Now, it wasn't actually the case. Let me see how many I've got here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That many rabbits. It actually wasn't true. So after 10 years, which is about 1870, they didn't have that many rabbits. And one thing that'll happen with population, if you do any sort of studies of it, it'll start going up exponentially, but then it starts to curve off. And a couple of the natural limiters here, do you remember what these lines are called? Asymptotes are food. So if we run out of food, they stop breeding, and also space. So Australia is an island. I'm not suggesting that it was entirely covered by rabbits, but it started to be the case where their population did start to slow down a bit. Now, there can be confusion about whether to use n or n-1 in the formula. If there's no context, it's n-1. So if it's just a basic sequence question, but the minute they put it into real life situations, quite often it can be n that we use in the formula instead of n-1. A little quick rough guide is if it says after or at the end of the year, then you use n. If it says at the beginning of the year, then we use n-1. Let's have a look at an example of that. Compound interest is an example of a geometric sequence. We've got an amount of money, we multiply it by 1 plus r, in the case of compound interest, to the power of n, not n-1. Leah invests $1,200 and interest rate is 6% per annum, compounded annually. What is her investment worth after 6 years? So at the end of the first year, it's worth 1,200 times 1.06. At the end of the second year, it's worth 1,200 times 1.06 squared. And so using our geometric sequence formula, it's going to be 1,200 times 1.06 to the power of 6. Okay, see this after 6 years, and it's 6 here, not 5. That's because we're adding on, or multiplying by really, 6 years of interest. If it said at the beginning of the 6th year, we would use the 5. This is probably the hardest bit to get your head around. Our answer is going to be 1,200 times 1.06 to the power of 6, which is $1,702.22. So here's a past exam question. A city is concerned about pollution and decides to look at the number of people using taxis. At the end of the year 2000, there were 280 taxis in the city. After n years, the number of taxis T in the city is given by T is equal to 280 times 1.12 to the power of n. Find the number of taxis in the city at the end of 2005. Right, we can see straight away that we've got n, not n-1. So when we want to substitute in for here, are we going to put in n is 5? Or is it going to be 4? Or is it going to be 6? If you're confused, drop a table. So at the end of the year 2000, there were 280 taxis. That's the beginning of the year 2001. So this is our first term. Second term, third, fourth, and fifth. So yes, we're definitely going to put in 5. So substituting it in, I get 280 times 1.12 to the power of 5, and that's going to be 493. Part 2, find the year in which the number of taxis is double the number of taxis there were at the end of 2000. Okay, so in this case we're going to put double the amount, which is 560, in here. Okay, so again, what we can do here is solve by using the equation button in your graphics display calculator, or you can use logs, or you can use guess and check. It's tidying it up a bit and using logs, which I did. N is equal to 6.1 years. Now let's have a think about what that means. So at the end of 2006, there's not quite enough. Okay, in fact, if we do that, it's probably a good idea to check it. 280 times 1.12 to the power of 6, we've got 553 taxis. So it's actually going to be in 2007 that we pass the double amount of taxis mark. Okay, let's move on to series. A series is the sum of the terms of a sequence. And there are finite sequences, so they stop, and infinite sequences that go on forever. We can calculate the sum of all finite sequences, but with some infinite sequences, the sum will converge. And this reminds me of quite a famous mathematical joke, which says, an infinite number of mathematicians walk into a bar. The first one orders a beer, the second one orders half a beer, the third one orders a quarter of a beer, and the barman says, you're all idiots, and pours 2 beers, because this sequence here, half plus a quarter plus an eighth plus a 16th plus ... never is more than 1 beer. So he saves himself a lot of bother and just pours 2 beers. Before we move on though, I need to go through sigma notation with you. So we write u1 plus u2 plus u3 plus ... plus un like that. Now, I know it looks scary. It's not too bad really. This means the sum of. You've seen that before in statistics. And here's our general term, or our kth term in this case. And this says start at 1 and go up by whole numbers, 1, 2, 3, 4, 5, 6, until you get to n. So there's the first one, put 1 in, add it to the second one, we put 2 in, then put 3 in, etc., up until n. So suppose we want to find this here. So here's our general term, k squared. We want to start at 1, then we want to put 2 in, 3 in, 4 in, and stop at 5. So it's going to be equal to 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, which is equal to 55. Here's an example. Write the sum of n terms of the arithmetic sequence 1, 3, 5, 7 in sigma notation. So we want to write it like this. Now you can see here that I'm not using un here. This is still going to be the general term, but I've got to use another pronumeral because I need sort of like an index, if you like. So it starts at 1, then goes 2, 3, 4, 5, up to n. So it wouldn't make sense to put un in here. But what we've got to do now is work out the general term. We know that the first term is 1, and it's got a common difference of 2. So working it out, I've got u1 is equal to 1, d is equal to 2, and n is going to be equal to k. And if we tidy that up, we get 2k minus 1. And so instead of this, I'm going to write it like that. So that's how we write the sum of n terms in sigma notation. So how do we sum the numbers from 1 to 100? You've probably done this as a puzzle sometime in the past. Hopefully you remember that you pair them up like this. So 1 and 100 makes 101, 2 and 99 makes 101, 3 and 98 makes 101, and there are going to be 50 pairs of them. So it's simply going to be 50 groups that each add to 101, so 50 times 101 is 5,050. We could write this as a formula like this. So the sum of n terms is equal to n on 2. That's the 100 divided by 2 here. First term plus the last term. Okay, and that formula is given for you on your formula sheet. But we know that this is equal to that. That's our nth term. So let's substitute this in here. And just tidying it up, we're going to get another version. So this is also given for you on your formula sheet. So this time I've got n on 2 outside of 2 times the first term plus n minus 1 times the common difference. So Let's return to Claire. Remember, she's learning to drive. Her first lesson's 30 minutes, her second lesson's 35, and each one goes up by 5 minutes. How many hours of lessons will Claire have completed after her 21st lesson? Okay, so in this case, we want the sum of 21 lessons. So N is 21, A is 30, D is 5. Let's put it in the formula. So I've got 21 on 2 outside of 2 times 30 plus 20 times 5. And then in the calculator we get 1,680 minutes. I think we'll change that, and it's 28 hours. E. During which lesson will she complete a total of 50 hours of driving lessons? So this is one of those questions where we're going to put the 50 hours in as the sum and then try and figure out what N is equal to. I've got an added complication here because these are in minutes and this is in hours, so I'm going to times that one by 60 to make that in minutes as well. It would be awkward to change these into hours. Alright, so tidying this up, we get N on 2 outside of 60 plus 5N minus 5 is equal to 3,000. Okay, so taking the 2 over here and tidying this up in here, I get this. Expanding and then taking the 6,000 over here, I get a quadratic. And let's tidy up a little bit more, divide everything by 5. Okay, probably going to need to use the graphics display calculator to solve this because otherwise you'd need the quadratic formula, which you would need the calculator for anyway. So put it into the polynomial solver and we get N is either equal to 29.5 or negative 40. The negative 40 is a stupid answer, so we can disregard it. And let's think about this. It's after the 29th lesson, it's during the 30th lesson that she will complete 50 hours. So there's our answer. Here's another simultaneous equations question, but this time with the sum formula. The sum of 8 terms in an arithmetic series is negative 16. If the 8th term is equal to negative 9, what is the sum of 10 terms? Now, we can't just add on negative 9 twice. We don't know the common difference. We're going to have to form a pair of simultaneous equations. So sum of 8 terms, let's substitute that into the formula and make it equal to negative 16, like this. So you can see what I've done here. I've got n over 2, so n is 8. 2 times the first term, we don't know it, plus this is n minus 1, and multiplied by the common difference, we don't know that either, is equal to negative 16. Just tidy this up a bit, that's 4, and bring it over the other side, and we've got our first equation. Then we also know that the 8th term is equal to negative 9, so substitute that into the term formula. So U8 is equal to U1 plus 7D equals negative 9, and so there's our second formula. What we can do here, just looking at these two, if I subtract this one here from this, the D's will cancel out. So subtract, I get U1 is equal to 5. Substitute it back into either one. 5 plus 7D, I've gone into here, is equal to negative 9. Take the 5 over. 7D is equal to negative 14, D is equal to negative 2. So always then look back to see if we've answered the question. No, we haven't. What is the sum of 10 terms? So now we're just going to put in the formula. We know U1 is equal to 5. We know D is equal to negative 2. And into the formula, 10 on 2, 2 times 5 plus 9 times negative 2 is equal to negative 40. Now the sum of the geometric series can be found using either of these formulas. So it's either like this or it is like this. And you can see the only difference is whether the r's are at the beginning or at the end. And we use this formula if r is bigger than 1 or less than negative 1. And we use this one if it's a fraction basically in between negative 1 and 1. And that'll just help you with negatives. It's not really that important. You can use either formula. Here's an example. Find the sum of 10 terms of the series 1, 2, 4, 8. So first term is 1. The common ratio is 2. Can you see how it's doubling each time? And n is going to be 10. So in this case we're going to use the formula that's got the r at the front. So there's u1, r to the power of n minus 1 on r minus 1. In the calculator gives us 1023. Here's another example. Find the sum of 15 terms of the series 6, 3, 1.5. First term is 6. Common ratio, what's happening? It's being halved each time. If you get stuck on that, do this one divided by this one. 3 over 6 is a half, and n is 15. This time I'm going to use this formula with the r's at the end. First term, bracket, 1 minus 0.5 to the 15 over 1 minus 0.5. It gives us 11.9996. What's the sum to 20 terms? So I'm just going to change this to 20. 11.9999886. What do you think the limiting sum is? That's the amount that the ceiling, if you like, that it can't get past. Does it seem reasonable that it might be 12? It is 12. So, if a geometric series has a ratio less than -1 or greater than 1, then the sum is going to diverge. So what it'll mean is it's just going to go up and up and up and up and up forever and ever. It never will have a ceiling. But if it has a ratio between -1 and 1, so it's a fraction, then the sum will converge. And in that case, it's going to go like this. And we can use this formula to find the limiting sum. So it's very similar to the one before. It's got no n in it because we don't have a number of terms. We've got number of terms, we've got infinity. So u1 over 1 minus r. So here's our question from before. Find the sum to infinity of the series 6, 3, 1.5. u1 is 6, r is 0.5 into the formula, and our guess was correct. The limiting sum is 12. Here's an example of where we can write a recurring decimal like 0.444444 as a fraction by using the sum to infinity of a series. So let's start with this 0.4 repeater and write it as a series of fractions. So it's 4 tenths plus 4 hundredths plus 4 thousandths plus 4 10,000ths, etc., etc. And that is a series, isn't it? And it's a geometric series. What's happening each time? What am I doing to this to get this? I'm multiplying it by 1/10. Can you see that? First term is 4 over 10. So u1 is 4 over 10, r is 1 over 10. Let's put it into the formula. 4 tenths divided by 1, take away 1/10, that's 9 tenths, is 4 ninths. So 0.4 repeater can be rewritten using this method as 4 ninths. So I just want to reinforce this. A series will only converge and have a limiting sum if r lies between -1 and 1. Another way of writing that is like this. So absolute value of r is less than 1. So which of the following series have limiting sums? 1 plus 2 plus 4 plus 8. This has been multiplied by 2 each time. So r is 2. So that's greater than 1, so no. This one here is arithmetic. It's not even geometric. It goes up by 1 each time. There aren't any arithmetic series that have a limiting sum, only geometric ones. So this one's no. What about this? I'm halving each term as I go along. So r is a half, and that's less than 1, so yes, this one will have a limiting sum. And then finally this one. What's happening here? 8 minus 6 plus 4.5. If you're stuck as to what the common ratio is, we go minus 6 over 8. That's -3/4. Now let's check it out. Let's do -6 times -3/4. Yes, that's 4.5. So -3/4 is in between -1 and 1. So this one also has a limiting sum. Just before we finish off with an exam question, here's the formulas that are given for you on the formula sheet. So we've got the nth term of an arithmetic sequence. We have both versions of the sum of n terms, so the one where you're given the common difference and the one where you're given the nth term. We're given the nth term of a geometric sequence, and you're given both versions of the sum of n terms of a finite geometric sequence. So the one where the r's first and the one where the r is second. And then finally you're given the sum of an infinite geometric sequence. Here's a past exam, and this incorporates both arithmetic sequences and also geometric sequences, and it's quite a difficult question. So the sums of the terms of a sequence follow the pattern. S1 equals 1 plus k, S2 equals 5 plus 3k, S3 is equal to 12 plus 7k, S4 is equal to 22 plus 15k, where k is an element of z. What's z again? It's integers, so they're whole numbers. Part A, given that u1 is equal to 1 plus k, find u2, u3 and u4. Okay, the first term, 1 plus k, is the same as the sum of 1 terms. The second term is going to be retrieved from this. So the sum of 2 terms is going to be the first term plus the second term will equal that. Okay, sum of 2 terms is equal to the first term plus the second term. We know the first term and we know the sum. So let's substitute that in and let's solve for u2. So u2 is going to be 4 plus 2k. Now we want to find u3. It's going to come from here. So the sum of 3 terms is going to be the sum of 2 terms plus the third term. We know this. It is there, 5 plus 3k, and we know sum of 3 terms, it's that. So we just need to put it in and solve for u3. And then finally, doing this one here, the sum of 4 terms must be the sum of 3 terms plus the 4th term. We know this, it's there. We know this, it's there, substitute in, solve. So the 4th term is 10 plus 8k. So our sequence is 1 plus k, 4 plus 2k, 7 plus 4k, and 10 plus 8k. B. Find a general expression for un. So here are our terms, our 4 terms. Now, the thing with this question is the sequence has an arithmetic part and a geometric part. So you can see this 1, 4, 7, 10. That's arithmetic. It goes up by 3. Now have a look at this. K, 2k, 4k, 8k. That's geometric. It's been multiplied by 2. So we're just going to do them separately and then add them together. So here's our arithmetic part. First term is 1. We don't know n. Common difference is 3. Tidying that up, we get 3n minus 2. So that's going to account for the 1, 4, 7, 10. Now let's do the geometric part. So in this case, the first term is k and r is 2. Substituting it into the formula, first term multiplied by 2 to the power of n minus 1. And so altogether, the general term is going to be 3n minus 2, that's our arithmetic part, plus k times 2 to the power of n minus 1, that's our geometric part. That's quite a difficult question. So I haven't seen one like that since or before, but I thought I'd go through it with you. So that brings us to the end of the content for this topic. But before we go, you might remember this sequence I showed right at the beginning, and you might have been curious as to what sort of sequence it is. As we look at it, it's not arithmetic. I'm not going up by the same amount each time. It's not geometric either, because I'm not multiplying by a common ratio. But there is something interesting about it. So I go from here to here, I times by 2. Going from here to here, I times by 3. And here, times by 4. And then here, times by 5. So it's pretty easy to get the 6th term. I just do 120 times 6, which is 720. Now, writing the nth term for this sequence is way beyond the course, so we're not going to worry about that. Okay, so that brings us to the end. Go and do a little bit of revision and some practice, and particularly past exam questions, so you get an idea of what sort of questions they're going to ask.